Hello everyone and welcome to today's cloud coaching session. Today I'll be talking about the machine learning capabilities of Oracle Analytics platform, and we will also look at in detail one of the ML algorithms, that is naive Bayes. So let's get started. My name is Rakesh Chhoria. I am part of the EMEA data platform specialist team working primarily on analytics. The standard safe harbor statement, I would give 5 to 10 seconds to go through it. So today's agenda would be, we will talk about the machine learning features that are available in Oracle Analytics and then understand one such ML algorithm, which is naive Bayes. So what is it based on? What parameters are available? And we will also look at the model quality of the machine learning model that is built. And then I'll walk you through the demo. So to start with, let's look at the various machine learning features that are available in Oracle Analytics Cloud. So primarily, there are three types of machine learning models that are available. So the first one is Oracle Analytics Cloud predictive models. This is nothing but the machine learning models that are inbuilt within the Oracle Analytics Cloud platform, and they can be built from within the Oracle Analytics Cloud interface. So typically you would train using historical data to build a machine learning model and then test the quality of the model by using some test data. And once you are satisfied with the machine learning model, you will apply it. All of this happens within Oracle Analytics Cloud. The second type is the Oracle machine learning models that you can leverage from Oracle Autonomous Data Warehouse. So typically we have a feature called as AutoML, where when you use this option of AutoML, actually the training and testing of the machine learning models will happen in the database, and then you can apply it in Oracle Analytics Cloud. And the third category is OCI machine learning models, where you have the machine learning models already built using various OCI ML services. So these pre-built models can be registered in Oracle Analytics Cloud, and then you can apply it on the test data. In today's session, we will focus about the Oracle Analytics Cloud predictive models that come inbuilt within the Oracle Analytics Cloud platform. So Oracle Analytics, the machine learning capabilities primarily caters to the citizen data scientists. It supports both supervised and unsupervised learning, and we use the feature of data flow to train and build the machine learning models. Now, machine learning model building is supported for numeric prediction, classification, both binary and multi, as well as clustering. So before we get into the details, first maybe let's look at the high level. What is supervised learning? So supervised learning describes a class of problem that involves using a model to learn a mapping between input examples and the target variables. So what it means is we already have historical data in which we have this relationship established. Say there would be a set of input columns or data points, and then the target variable that we have. And then the historical data actually gives us a relationship between these two. And you use the machine learning model to discover it and then apply it on new data set where you want to predict the target variable. Some of the common algorithms used for supervised learning are naive Bayes, CART, neural network, linear regression, and support vector machines. Some of the use cases or examples of where supervised learning is used is you want to do sales forecasting, you want to classify transactions as fraudulent or not, or you want to predict real estate prices based on certain attributes that you have in the data set, right? So all these can be classified or come under the category of supervised learning. Unsupervised learning. So this describes a class of problems that involves using a model to describe or extract relationships in data. So what this means is we have data points with us, but we don't know exactly the relationship between them. But we want to use the machine learning to identify maybe which are all the data points which are closed or which exhibit similar behavior, right? So common algorithms for this kind of learning are k-means and hierarchical clustering. Some of the examples could be customer segmentation, or you want to do something called as inventory grouping or market basket analysis. Even if you want to develop recommendation systems, this is where you will use unsupervised learning. Moving ahead, Oracle Analytics machine learning algorithms. So these are all of the algorithms that are available within Oracle Analytics Cloud at your disposal. So where for say numerical prediction, we have elastic net linear regression, random forest, linear regression, CART. For multi-classification, we have SVM, CART, naive Bayes, neural network, random forest. For clustering, we have k-means, hierarchical clustering. For binary classification, we have logistic regression, SVM, CART, naive Bayes, neural network, random forest. And today we will focus on one machine learning algorithm, which is naive Bayes. Now, naive Bayes is a supervised learning-based classification problem for which we will use naive Bayes, and it can be used for both binary and multi-classification. Okay. So moving ahead, what is naive Bayes algorithm? It is an algorithm based on conditional probabilities. It uses the Bayes theorem, and the formula for using the Bayes theorem is, suppose there are two events A and B. What is the probability that event B will happen given that A has happened? So that is what we call as probability B given A. And it is calculated as the probability of events A and B happening together, and it is divided by the probability of event A happening independently. Okay. So the important part is independent. So here what we call it as A as the independent variable and B as the dependent variable. Okay. Now let's take an example to understand this probabilities formula. Suppose I want to predict how many customers under the age of 30 would buy a car. Okay. So in this case, my event A is customers under the age of 30 and event B is buying a car. Now let's say, example, I have a data set of 100 customers with me, out of which there are 25 such customers who are under the age of 30 and have also bought a car. So in this case, my probability of a customer buying a car and being under 30 would be 25 by 100, which is 25%. Now, let me take the case of, out of the 100 customers that I had, say 75 customers were under the age of 30. So that is the probability of A. Now, probability of A is 75 by 100, which is 75%. Now, if I have to calculate the probability that a customer under the age of 30 would buy a car, it would be 25 by 75, which is 33%. So this is how you calculate the probability of a particular event given a certain other event has happened. Now, naive Bayes as an algorithm assumes that each predictor is conditionally independent of the others. Now, say if you have 10 or 15 attributes in a data set, right, and you have one target variable. Now, it will calculate the probability individually for each of these, and to get a combined probability, it will do a multiplication of the probabilities. So that way, you can consider that each attribute is conditionally independent of the other. Okay. So what are the advantages of using naive Bayes algorithm? So the naive Bayes algorithm is a very fast, highly scalable model. Okay. It can be used on large dimensional data sets. Okay. A data set which has large number of attributes. Okay. Second thing is it does not require large amounts of data to train and build a machine learning model. Okay. It can handle both continuous and categorical data, meaning numeric as well as text data. Okay. From a build perspective, the naive Bayes supports parallel execution. So that way it is faster. Okay. And as I had mentioned earlier, naive Bayes can be used for both binary and multi-classification problems. Now let's look at, when you build a machine learning model, there would be a set of parameters that you need to configure and then build a machine learning model. Okay. Now let's look at the parameters of this particular algorithm that are available in Oracle Analytics Cloud platform. So the list of parameters are target, positive class in target, categorical column imputation, numerical column imputation, encoding method, maximum null value %, and train partition %. We will look at each of these parameters in the coming slides. So the first parameter is target. So target is nothing but when you have a data set, right? What is the target column or the variable on which you want to build a machine learning model? So suppose in a data set that you have, you want to see how likely is a customer going to buy a particular product or not. Say likelihood to buy. Okay, it can have two outcomes, yes and no. Okay, so in that case, the target column is likelihood to buy. So this is where we are trying to build a machine learning model. The second parameter is positive class in target. So as I've taken a simple example of say likelihood to buy, and there are two outcomes, yes and no, right? So which of these values is actually a positive value in the target? Okay. So it can be yes in our scenario. And in some cases, when you are predicting, say with numerical columns, 1 and 0. So 1 can be positive, 0 can be negative class, right? So 1 you can define as positive class. Now, if you are in a situation where you are doing multi-classification, so a column will have more than two values, right? Let's take an example of sentiment analysis where say you want to identify the emotion of the tweet, and the emotion can have three values: positive, negative, and neutral. So out of these three values, which of the value is actually a positive value in the target class? Okay. So that's how you will set this parameter. Moving ahead, the third parameter is categorical column imputation. So this is an important data preparation kind of a step where, so many times what happens is when we deal with historical data or training data to build a machine learning model, what is observed is that most of the columns will not have data. When I say columns will not have data, they will not have data for all the rows. Okay. So many times it happens that you have a lot of attributes, but most of the attributes in rows, you will not get data. So there would be typically null or any kind of thing. So for any text or string related columns, okay. So what you are using this particular parameter to say is, if I encounter such a scenario where say there are nulls or NAs in a particular text column, how should I replace that null value? So there are two options available: most frequent and least frequent. So what it will do is, based on the values that are available in the column, it will take the most frequent value and replace this value with, say, from null. Whichever column has null, it will replace that value with the most frequent value. If you set it as least frequent, it will do it as least frequent. So let's take an example. Maybe you have a column called as occupation. Okay. And to keep it simple for explanatory purposes, let's say we have three values. You are salaried, self-employed, okay, or not working, salaried, self-employed. Now these are three values, right? Now you can have many rows of data where you have not captured the value for this particular column, occupation. So what you will do, you have to now take a call whether you want to replace it with the most frequent or least frequent value. Let's say salaried is the most frequent value and not working is the least frequent value. So based on the data set nature of data, you can take a call and configure this parameter as most frequent or least frequent. The default value is most frequent. The next parameter is numerical column imputation. So this is again a parameter where you need to set a particular value, and this applies for all of the columns in the data set which are of numerical nature, numbers, numeric in nature. Okay. So the possible values are mean, maximum, minimum, and median. And the default value is mean. Here again, the idea is to not have any or null values in the data set and try to populate them with reasonably closer data points so that when you build a machine learning model, you have a better quality of the model. Moving ahead, the next parameter is encoding method. So for encoding method, two options are available: indexer and one hot. But before maybe getting into the details of each of these options, why encoding is needed? Encoding is needed because most of the machine learning algorithms work very well with numbers, not so much with text. Okay. So what happens is, suppose you have a column. Again, let's take the example of occupation. We have three values, right? Salaried, self-employed, and not working. Correct? These three values in a column. Now, what the machine learning model will try to do is it will encode these values with numbers so that the processing gets easy when it is trying to build a machine learning model. Now, as I mentioned, there are two methods here, indexer and one hot. So the indexer method, what it will do is it will replace each of the unique value with an index. So say it gives 1 as an index for salaried, 2 as index for self-employed, 3 as index for not working. Okay. Now what it will do is it will replace each of the values in each of the rows with these values 1, 2, 3, and then use it for processing. So that is the indexer parameter for encoding. The other parameter is one hot. One hot, usually what it will do is, based on the number of distinct values, it will actually create new columns in the data set. So similarly, if we talk about occupation as an example, it has three values, right? So if you choose the encoding method as one hot, what will happen is it will actually create now three columns, and the column names would be something like is salaried, is self-employed, is not working. And this column will be populated with values as 0 or 1 based on the value in the actual data set. Okay. So let's take an example of one row where the occupation was salaried. So in this case, the column is salaried will have the value of 1, and then is self-employed will be 0, and is not working will be 0. So this is the another way of doing encoding, indexer and one hot. The default is indexer method. Moving ahead, the next parameter is maximum null value %. So this parameter is configured to check the number of allowed null values in the column of a data set. See, when we are trying to build a machine learning model, it doesn't make sense if most of the columns, most of the data points are null. Then we will not be able to build a good quality model, right? So this parameter helps us to say how much of null values in a particular column you are allowing. So in this case, the default value is 80%, and you can configure any value between 1 and 100%. So now when we say the default is 80%, what does that mean is, if say a particular column, again, let's stick to the example of occupation, right? So we have more than, we have around say 80% of rows where we don't have a value captured, right? So if it crosses 80%, then that column will not be considered to do model building, okay? Because it has exceeded the threshold. So this again ties back to the previous two parameters on imputation that we did, right? Both categorical and numerical. So these go hand in hand. So if the number of allowed values are less than the maximum null value % setup, then what it will do is first it will check for this parameter. And if it is under this limit, then it will replace those values with whatever options we have chosen, like say for categorical, most frequent or least frequent, and then for numerical, mean, median, min, or max, whatever is the value. So that is how this parameter is important. Finally, we have a parameter called as train partition %. What it determines is it determines the % of input data that is split between train and test data. So what does this mean is, suppose you have a data set of 1000 rows, which you have used as training data set to build this machine learning model, and you are configuring all of the parameters. So what it will do is, again, the default value is 80%, and then this parameter can be set anywhere between 10 and 100%. So what it means when we say 80% is, 80% of these 1000 rows, the training data set that we are using, will be used to train and build the model, and the remaining 20% will be used to test the model's quality. Okay. So now if you set it at 70%, then what happens is it will use 70% of the training data set. So 700 rows out of the 1000 rows. And then once the model is built, it will actually test the model on the remaining 300 rows of data and then give you the model quality. Okay, how good is the model quality? Because you also, once you build the machine learning model, the next important part is to check the quality of the model. Okay, and based on the quality of the model, you might have to come back and tune the parameters, change the values a little, and again try and rebuild the machine learning model so that you check for the quality, and then you take a call. Okay, now this machine learning model is of a acceptable quality and it is ready to be deployed. Okay. So moving ahead, when I talk about model quality, now we'll stick to this particular algorithm naive Bayes, right? And as mentioned, it is used for classification. So what you see here as a screenshot is a confusion matrix for a binary classification scenario. Okay. So essentially what the table is trying to do is there are actual values 1 and 0 and predicted values 1 and 0. And it is trying to split the predicted results on the test data that we have within the machine learning model building exercise, right? It is trying to give us on the test data when this machine learning model was built, how are the outputs comparing? Okay. So how to read it would be, so the actual values 1 and predicted values 1 means the actual value was 1 as well as the machine learning model predicted as 1. So this is what we call as true positive. Okay. So in this case, it's around 147 out of 628 rows where it has predicted 1 and 1. Similarly, if you look at the cell where it says 0 and 0, again, same situation where the actual value is 0 and the machine has also predicted the value as 0. In this case, it is 279 out of the 628 total rows. Now, similarly, there are scenarios where the actual value is 0, but the predicted value is 1. So in our case, the value is pretty high. It's 201. Whereas the other scenario where the actual value is 1 and the machine has predicted it as 0 has happened only in one instance, 1. So these are your base KPIs where what we say true positive, true negative, false positive, and false negative. Now, using these parameters, we actually calculate different model quality related parameters and then determine the quality of it and then decide whether it is acceptable or it needs to be rebuilt again by changing certain parameters. Okay, or maybe working on the data set, removing some columns or things like that. Okay, those would be the tuning techniques. So now, what is model accuracy? So model accuracy means true positive plus true negative divided by total observations. So in our case, it would be something like 147 plus 279 divided by 628, okay, which comes to around roughly 68%, as can be seen in the screenshot. Now, in earlier times, model accuracy was kind of the only quality parameter that was looked at to determine how good a ML model is that is built, right? But over a period of time, people have realized that in scenarios where, say, the data set is skewed, okay? So suppose we are talking about, in this case, we are, say, talking about affinity card or likely to buy, right? So the possible values are 1 and 0, but more than 90% of, around 90% of your data is having 0 and only 10% is having 1. So this is a very skewed scenario. So now what essentially happens is, if the machine learning model built predicts, say, for 95 out of 100 as 0 and only 5 as 1, still the accuracy will be very high because the actual in the data set is 90, the machine learning model predicted 95, correct? So the false positive rate would be just 5 by 100, 5%, which we might think is acceptable. So because of these considerations, additional parameters like precision, recall, false positive rate, and F1 score have been added. So the formulas for precision are true positive divided by true positive plus false positive. Recall is true positive divided by true positive plus false negative. False positive rate is false positive divided by actual number of negatives. And then F1 score is calculated as 2 times multiplied by precision star recall divided by precision plus recall. So for the above machine learning model quality that you see, so the formula would be something like this. So model accuracy would be the numbers 147 plus 279 divided by 628. Precision would be 147 divided by 147 plus 201. So as you can see, the accuracy is high at 68%, but the precision is very low. It is at 42%. And the recall is very good. Okay, it's almost at 99%. And we have a very high false positive rate. So false positive rate is where the machine learning model is predicting it as a positive outcome, whereas in reality, it is a negative outcome. Okay. Now, based on the use case and the scenario that we have, we can think which parameter at what percentage might be a good thing. Okay. So say, suppose you want to do a campaign where based on this machine learning output, you will get a list of customers who are likely to buy a new product. Okay. So in that case, if you have, say, a false positive rate of 10 or 15%, it is okay because you are reaching maybe little more customers. Okay. And then seeing whether the campaign will be a success or not. But if in scenario, if the false positive rate is more than 50%, right? So that means what happens, even though you are relying on this machine learning model, most of the customers you will reach might not buy the product. Okay. So that will make the campaign ineffective. So each of these parameters as a combination, you need to evaluate the different values and then take a call on whether the machine learning model that is built is okay for usage or it needs to be tuned further. Okay. So with this, we will move into the demo. So the scenario for the demo is we will use a sample data set, user demographics data, certain attributes of users, and try and build a machine learning model to predict if a customer is likely to buy an affinity card, loyalty card, yes or no. Okay. And then we will verify the quality of the model, and then we will understand the parameters and tune the model in iterations. Okay. So let's get into the demo. So as I had mentioned, we will use the feature of data flow within Oracle Analytics Cloud to build a machine learning model. Okay. So now to access the data flow, what we will do is onto data flows. We'll click on the create data flow. So first is I need to identify a training data set which I can use to actually build the machine learning model. So for my case, as you remember, we have talked about customer data, training data set that we will use to identify whether a customer is likely to buy an affinity card or not. Okay. So this is how the data set looks like. I have these almost 14 columns, customer ID, affinity card with values as 0 and 1. 0 meaning the customer has not bought the affinity card, whereas 1 meaning they have purchased it. And we have bookkeeping, bulk disk packets, comments, education, and so on and so forth. These are the different data set parameters that we have. This is our training data set, which we will use to actually build the machine learning model. So in our case, as we want to build a machine learning model for affinity card and it has two values, okay, we will use the binary classification. So what we will do here is we will click and say train binary classifier. So for this, out of the box, Oracle Analytics Cloud, as I mentioned in the presentation slide as well, there are 6 different algorithms. Okay, so we will use naive Bayes for building this machine learning model. So as you can see, the model training script now is naive Bayes for classification. So the first parameter was target. So here we need to select a column. So in our case, it is affinity card. So we'll select the column. So now the positive classing target is value 1. Okay, by default it was yes, but because we know in our data set we have 1 and 0, we will set the value as 1. Now for the first iteration, we will leave all of these parameters with the default value. So you can see for categorical column, it's most frequent, numerical column, it is mean, encoding is indexer, maximum null value percent is 80, and train partition percent is also 80. Okay. So all I'll do is I'll give a name to the machine learning model. Okay. So I can call it as naive Bayes affinity card version 1. Version 1. Okay. Now all I need to do is I need to save this data flow. Now once the data model is saved, I'll just click on this run icon, run data flow, where now the data flow is running, and now Oracle Analytics Cloud is trying to build the machine learning model. So this is the interface how you will build a machine learning model. So while the process is running to build the machine learning model, you will have your training data set, say, right? So usually the best way to have a training data set is to identify a representative sample of the data set, okay, and use it to build the machine learning model so that the machine learning model that it gets built is of reasonable quality. And as I had mentioned about the parameters, right, that's how we will do the data prep. So some of these data prep activities in terms of replacing nulls with certain values and all are done using the parameters within the Oracle Analytics Cloud interface. Okay. Now, many a times it happens. So in our case, I've taken a simple example with just 14 columns, right? But in reality, in real use cases, you might have data set with large number of attributes. While naive Bayes works very well with large dimensional data sets, okay? Many a times, based on your domain knowledge and expertise, you can actually understand, because you understand the data very well. You know which columns might be of use, which might not be of use, or sometimes it could be even that you have some dependent columns within the different set of data sets, right? So you can actually even select the list of columns that you want to use to build the machine learning model. So now in our scenario, the model is now ready. Okay, so that's how simple it is. You don't have to write any complex SQL or write any Python code to build a machine learning model. So this is a feature, very, very powerful feature, which can be used by citizen data scientists. So by citizen data scientists, we mean the business analysts and power users of the system who understand the data very well. Okay. And now they have a very easy to use UI to build a machine learning model and take their analysis a little further. So they don't have to wait for somebody from the data science team to write a complex machine learning model. Because see, most of the times data scientists might not have that much deep domain knowledge about the data sets, right? So it's always a combination. So Oracle Analytics Cloud tries to help the business analysts build these machine learning models and then maybe ask better questions. Okay. So now let's look at the quality of the model that is built. Now the machine learning model that gets built will be under a tab called machine learning. Okay. So here you can see this is the Definite card version 1 that got built. So what we will do is we will inspect and check the quality of the model. Okay. So the quality of the model is looking something like this. So where we have a model accuracy of 58%, precision is 35%, recall is 92%, false positive rate is 53%, and the F1 score is 0.51. Okay. Now clearly we see that false positive rate is high. The model accuracy is also not that great. Okay. And the precision is also very low, 35%, right? Now let's look at how we can tune a certain parameter or a set of parameters and see how we can improve. Okay. Now as part of this demo, what I'm trying to show you is how you can tune the machine learning models with the different parameters that are available. Okay. So now let's come back to the data flow that we built. Okay. So now what we will do is we will open the data flow once. Now, again, using the same data set, we have these, right? So what we can do is, first, we can try with the option of, say, instead of, for column imputation, instead of most frequent, we can try with less frequent, okay? And then I'll just save it and run the data flow again, okay? So while it will take a few seconds to a minute to run, so what I'm trying to do here is I'm trying to say that if there are nulls in a categorical column, instead of most frequent, use the least frequent value to replace it. Okay. Now, similarly, we could actually have done a number of parameters together. Okay. But just as a demonstration, I'm trying to show changing a parameter. Now, changing a parameter might improve the quality or might not improve the quality. Okay. That is also possible. Okay. So we have to play around with these parameters and also have a very good understanding of the data. And then based on it, actually, we can build a very good machine learning model. So while we wait for the model to build, so I think next what we will try and do is we will try and use we'll try to change the encoding method. Okay. Because what we know is it's naive Bayes, right? So it works with large dimensional data sets. So maybe instead of using an indexer, let's try and use one hot encoding method and then see how the model will perform. Okay, so the model is now built. Okay. So now let's look at the model quality to see how it is, whether there is any improvement or not. Let's look at it. So we see that there is nothing much, no improvement based on the change that we have done. Okay. So most of the quality parameters all are still same. Okay. Now, as I was mentioning, we'll come back to the data flow and then we will try and change the encoding method. Okay. So again, as this parameter didn't have any effect, I'll revert it back. Okay. And from indexer, I'll change it to one hot. And then just for reference, maybe I'll give a new name to this model so that I have both the copies of the ML model that can be saved, okay, for comparison. So now I'll save this data flow and run it. Now, essentially what we have done by changing the encoding method, just to give a recap while the process is running, is from the indexer method where, say, for the categorical columns, it would replace the values with an index kind of a setup 1, 2, 3, 4. In one hot, what it is trying to do is based on the number of distinct values, it will add new columns before processing or using the data set on to build the machine learning model. Okay. So let's see, because naive Bayes works very well with large dimensional data sets. So let's look at and see whether we see any improvement in the model that gets built or not. Okay, so the model is now complete. So now let's come back and look at the quality of the model that got built, version 2, right? We'll do an inspect of the model. Now when we look at the quality, yes, we see some visible improvement in the quality of the parameters where the F1 value from 0.51 went to 0.59. The model accuracy increased from 58% to 68%. Now the precision has gone up from, I think, 35 to 42. Recall has gone up from 92 to 99%. And the false positive rate has also reduced, I think, from somewhere 53 to 42%. So this is definitely an improvement in the machine learning model that we have built in this iteration when compared to the previous iterations. Okay. So this way, you can actually play with the parameters and then work on improving the machine learning model build quality. Okay. Now, as we have seen one thing, that the false positive rate is still very high. Okay. So this sometimes leads to us to understand what happens is, end of the day, naive Bayes is trying to do a probability calculation. And maybe a probability above a certain level is being treated as a positive class. But in our scenario, the positive class is getting impacted because we are getting a high false positive rate. So now let's try and see if we change the positive value in the class. Okay. So earlier we have told 1 is the positive class. Let's try and do 0 as the positive class. Okay. And then see how the machine learning model quality build improves. So this is again one more iteration where we are trying to see, because in this scenario, we are trying to address the false positive rate because it has come down from 53 to 45, but still it is very high, right? False positive rate. Okay. So now let's try and say, so I'll give a new version. Again, I'll save it as a different model. So I'll just save and run this data flow. So here, in a nutshell, what I've tried to do is, because I see an issue with the false positive rate being very high, I have tried to change the positive class value in the target variable from 1 to 0. So now what has happened is 0 has become the positive class in it. So where actually it means the customers who are not buying the loyalty card. Okay. And 1 would be the customers are buying a loyalty card. But we are trying to do this and see if there is an impact on the false positive rate. So let's give it a few more seconds for the machine learning model to get built. So again, while the model is getting built, all I would like to say here is machine learning model building is an iterative process. Okay. So based on the number iterations tuning that we do, we have to then evaluate the quality of the machine learning model that got built. And if we think it is reasonable or satisfactory to use this machine learning model on the actual data set that you want to deploy, then you can do that. And then again, maybe after a certain duration, because you would have got new data set now, right? Again, the idea would be to build a machine learning model again, tune it, improve it, and then deploy it again. So it's more of an iterative process that happens. It's not like we have built it once and it is available for lifetime. Okay. Because the nature of data, the data set, the attribute, values, all of the things change over a period of time. So it's always a good practice to periodically rebuild, reevaluate the model that you have built with the new data set. And again, end of the day, the quality of the data that you give to build a machine learning model would determine how good the model is. Okay. So now that the model is built, now let's check the quality of the model. Okay. So we have the version 3 now available. So now, as you can see here, the F1 value has gone up from 0.59 to 0.73. The model accuracy still remains at 68%, but now the precision has gone up. It has gone to 100% now. Okay, from 35 to 43%, it is now all the way up to 100%. The recall has also improved to 58%, and the false positive rate is drastically down now. So it has come down from, say, 43%, I think, if I remember correctly, 43, 44% to now 1%. Now, this could be a model that could be useful where, say, we want to build a machine learning model where we don't want high false positive rate. Okay. We are okay with the accuracy of 68%, but then we don't want a high false positive rate because we don't want to be reaching out to customers who are not likely to buy this affinity card or loyalty card that we are talking about, right? So again, based on the use case and the need, you can say which model is better for the data set and the use case that we have at hand. Okay. Now with this, model now available. Now let's look at how we can apply this machine learning model. Okay. So for this, what we will do is there are two ways to apply a machine learning model that you built in this way. So what we will do is the first approach is to create a data flow. Okay. So we will create a new data flow. Okay. Now for this, as I mentioned, I'll use a test data. Okay. So now the data set structure is similar to the one that I had used for training data set. Okay. I'll use this test data and then I'll try to compare the predictions of the machine learning model that got built and maybe compare it with the existing data set. Okay. So all I'll do now is I'll actually click on apply model. Okay. Now from this, I have these three different versions, right? So maybe I'll choose the version 2 for demo purpose. Okay. So where we had the positive class in target still as 1. Okay. Model accuracy was 68 and there was a high false positive rate, right? So we select the second version. We click on OK. So now what it essentially is doing is it is giving two outputs. Okay. Two columns as output, predicted value and prediction confidence. I'm just renaming it, predicted affinity card and prediction confidence. I'll leave it like that. Now, the other important part here is on the input parameters. Okay. So in my case, because the data sets are similar in structure and all, so it did a mapping of all the input to output columns. Now, if in your scenario, say you are using a test data where maybe the column names are different from the training data set that you had used, here you can do the mapping of which column of the test data maps to which column, input column that the model is expecting. Okay. This way we can do. Now, again, if you want to calculate things like lift and gain, that option is also available where if you say you want to calculate, you can select yes on the lift and gain and then select the column on which you want to do the lift and gain. Okay. So maybe I want to do it at just for demo purpose, maybe at education, I can do that. Okay. And positive class to compute lift. So for the education, what are the different values that you see? 10th, okay, HS grade. So maybe I'll give 10th. Okay, so this is how you can actually set up. Now, maybe for this demo purpose, I'll not do that. So I'll just remove this. Okay. And now I'll just save this new data that I have. Okay. So I'll give a name to this data. It is nothing but now you have the different values here. You can change them. If it is an attribute, by default, it takes everything that is of number type as measure, right? So we can do this here. So even say for the confidence of prediction, it's a measure, but I want to use average as the aggregation instead of sum because confidence is a percentage, right? So it always makes sense if you do an average instead of a sum. So now that I have given a name, okay, this data set, I'll save the data flow. Okay, now that the data flow is saved, I'll just give some time. I'll run this data flow. So this is how once the machine learning model is built, you can actually apply it on the data set, on the test data set that you have, save the output as a new data set. And then based on that new data set that gets created, you can actually compare the results and see. So this is again one more way of testing the quality of the model. Because in this case, the test data that we have also has the values, actual values of affinity card, right? So you can see how efficient is the model. You can do the comparisons with the test data. And then if you are satisfied with this, then this can be used on new data that comes in, say in your production systems or something, where you can use this machine learning model and build it and use it for the new data set or the production data set that you get. Let's give it a few more seconds. Few more seconds for the data set to get created, the predicted outcomes. Yes. So now the data flow is complete. Okay. Now what you will see here is if I come to data sets, I'll see that a new data set is created. Okay. So what I'll do is I'll just say create workbook. Okay. Affinity card. Okay. Maybe I'll just create one calculation first called Azure. And I'll just put a count function. Okay. Count distinct on customer ID. Okay. Validate the function and save. So now what I'll do is I'll use the customer's affinity card and prediction card and maybe build a pivot. Okay. So essentially what I'm doing here is I'm trying to recreate the confusion matrix, right? So here you have the actual values and the predicted values and how are the numbers looking like. Okay. So this is how I can actually evaluate the data set and then take a call on how good is this machine learning model, the quality that we have built, and use it accordingly. So this is one way of applying the machine learning model that has been built within Oracle Analytics Cloud. Now I'll show you the other way. Okay. Now the other way would be we will choose the data set that we want to use for testing, right? We have the test data. So what I'll do is I'll come here and say create, and I'll create a workbook. So now in this workbook, what essentially I will do is this is the test data that I have here. Okay. All I'll do is I'll say create scenario. So in create scenario, I need to select the machine learning model. Okay. So for this iteration, I'll select the version 3. I'll just click on OK. Now, once I do this, now the machine learning model is running behind the scenes, applying it on the test data that is there in this workbook. And then I have already got the results. Okay. Now, as I had done last time, I'll just create a new column called as customers. Okay. And I'll just give a count distinct on customer ID. Okay. I'll just validate it and save. Okay. So now let's look at the confusion matrix again. So customers, affinity card prediction, and actual affinity card. Okay. Now I'll do a pivot visualization on this. Now, as you can see, now this is the equivalent of confusion matrix that we generally looked at when we did the ML model quality inspection, right? So now this is actually an easier way for business users to apply the machine learning model that got built in the data flow and then use it in your workbook for your further analysis. To other machine learning algorithms. In other machine learning algorithms, you get a little wider set of parameters to tune, okay, to tune and play with. But for naive base, the essential thing would be the data, the data preparation, the kind of data. So if we give a good, rich quality of data to the algorithm, the better will be the quality of the model that gets built. Okay, so to give you one comparison, I had run these data flows some time back. Okay, so I have one predicted values. So you can build actually these rich workbooks and visualizations based on the predictions that you have done. Okay, so if you see here, this is how the predicted value and the actual values, this is the comparison. So the model predicted that out of the test data that I had, around 524 customers are likely to buy the affinity card. Now, if I look at, say, little more demographic analysis, right? So based on the number of people in the household, okay, we see that if the number of people in the household is 1, 2, or greater than 6, 8, or 9, then the chance of people buying this loyalty card is very less. Whereas if the household size is between 3 to 5, 3, 4, and 5, the chance is high. So this is actually a very good insight for us based on the prediction that has happened on the household size. So if it is less than 3 or more than 6 or more, then the chance of people buying a loyalty card is pretty less. Similarly, what you see here is the distribution of affinity card prediction as yes or no based on the occupation. Okay. So clearly we see that some of the occupations like executives, crafts, and maybe professor, sales, these are where the chance of people buying a loyalty card is higher compared to other professions. Okay. Where we say things like handler, transport operator, okay, farming, these all, the chance of people buying it are less. So this was a demo on the naive-Bayes machine learning algorithm, the different parameters that are available within Oracle Analytics platform, and how you can tune them to improve the quality of the machine learning model. Now that we have come to the end of the demo, I would just like to summarize what we have done as part of the cloud coaching session today. We understood what is naive-Bayes machine learning algorithm, what it actually does, what is the formula it uses, and then what are the different parameters that are available. And again, the use cases where this particular machine learning algorithm can be used to actually do predictive analytics, build machine learning models to do predictions. And with this, I come to the end of the session. Thank you for attending the session today.